So what is correlative
Array
tomography?
Yes.
Correlative array tomography is, simply put, a technique that reconstructs a 3D view of a sample by slicing and embedding it in different ways. This makes it possible to generate images in extreme detail. One of its main strengths is its versatility. Many techniques can be used together with array tomography. What exactly is array tomography?
So array tomography stands for a technique in which, imagine that you have a sample, usually that is a volume, if you think about it. So basically like a piece of tissue, right? And you want to be able to reconstruct a 3D view of that tissue. The issue is that there's a lot of techniques that cannot, let's say, penetrate from the surface. So if you try, you will only get an image of the surface. So what we have to do is that we take that sample, we embed it in different ways, in such a way that we can actually start slicing it, like if you are slicing a salami in a way, right? So you're going to slice it, and each slice you're going to deposit on a surface usually. And you have to do it very carefully, because you want to do it like the cards in a train. You want to put them one after the next. And then, depending on the method that you will use the technology to scan each one of those sections. And then via different sort of processing steps, we're going to take each section and we're going to reconstruct the volume. So we have to put them one on top of the other, right? So it's a demanding step in the analysis part, but then the results are beautiful because now we are able to reconstruct the volume. The correlative part is that we are going to use more than one technology. So in our unit, we tend to use a lot a correlation between light and electron microscopy, because light microscopy can have a lot of, let's say, chemical specificity. So it can tell you, for example, which parts of your sample are the disease area versus the healthy area and things like that. While the electron microscopy has a much higher spatial resolution and can give you more the context as to the intracellular morphology of basically that can give you information about what is the underlying causes of the disease as well. So that's the part where we're going to correlate, but in fact we can actually do this with many different types of technologies. So not only light microscopy, we can have more sort of chemical imaging, like mass spectrometry imaging. We can have really almost the imagination is sort of the limit, as well as the sample preparation, because we usually need to find a compromise when we make the sample in such a way that it can actually be used for the different methods, and then we can reconstruct the volume. I think that nowadays this has evolved a lot. It has proved to be a very valuable technique for many different, let's say, modalities or specialties in science. And also I think that the most valuable part is this idea that you can combine the benefits of different modalities, because you have this sort of holistic view when you put the different modalities together. And that basically means that it's extremely valuable not only in neuroscience and cell biology, but also nowadays we are moving us to a lot of studies in developmental biology, where we're going to try to see what are the fate of the different cell types and how they evolve and change within tissue. And also I think something that we find extremely interesting is the part of the pathology and clinical studies. So where we also think that this technology can offer a huge benefit for researchers within those areas, especially in the analysis of disease and treatments and so on and so forth. So I would say that the scope is becoming bigger and bigger, and I think our challenge as a unit is not only to provide very good services, but also try to show what is possible with the technology, so new ideas can pop out from different researchers.
Perfect, great.